Hi everybody, my name is Bhavishya and in this lecture we will learn about our type 2 LSA, right, which is our network LSA, right. But before this we have to recap of what we have learned so far. Okay, so the very first and the most fundamental important thing is our LSA, right, link state advertisement. So we have already saw how from init state to the full state, how it happens in so far we have saw everything, right? So the important thing here is to fully understand what is our type 2 LSA is the very first thing, that the difference between neighborship and our adjacency. So when we talk about neighborship, so let's suppose there is router 1 connected to router 2, right? So as you know, the very first step is init state, then the two-way state, right? Where we are able to see our own router ID in others hello packet, right? Then we transit from init state to two-way state. So that two-way state, when that two-way state is established successfully, so that two-way state is known as our neighborship, right? And then after our database description packet to our link state update to our request to acknowledgement, after all this, when we can see them in fully synchronized state, this is where after our full state, this is where we call it adjacent. This is when this is where we call them adjacent, right? That both of these are in adjacent state, right? So now you know the difference. And there is also one thing that says those router who are neighbor. So let's suppose this is in two-way state, right? So these are neighbors now. They're in neighborship for now. So those router who are neighbor can become adjacent, but without neighborship, they can't be adjacent, right? So neighborship is very important because it is a part of the process, right? In it two-way, and then at the end you see the full state, right? After all those process, after Xstart and all that. So yeah, in short, so this is so the conclusion that we got from here is, let's suppose R1, here we have R1 connected to switch, and then we have R2, then let's suppose we have R3 connected, right? So here in this topology, not every router will make adjacency with each other. Why? They should be doing it. Why they are not doing it? So the reason lies behind how it works and what is the purpose behind it. So let's suppose here we have three routers, right? So the total routers here is three, right? And the adjacency that they will form will be three, right? Adjacency form will be three here, right? What will be the adjacency with R1 will make with R2, okay, R1 will make with R3, great. R2 will make with R3, right? And vice versa, great. Now, if let me expand the topology. Let's suppose to form a formula out of it, like what is the relation between the total number of routers and adjacency form. So let's suppose we have four routers. Okay, let me just name it out. R1, R2, let's suppose R3 and R4. Now, as we have four routers, so the total routers for now, let's suppose, is R4, and we'll discover how many adjacency we are making, right? So R1 will make its adjacency with R2, great. R1 will make its adjacency with R3, great. R1 will make its adjacency with R4, great. Now R2 will make its adjacency with R3, yes. R2 will make its adjacency with R4, right? Yes. So far, how many adjacency we have? Okay, 1, 2, 1, 2, 3, 4, 5. Great. And now if you'll see R1, R2, R1, R3, R1, R4, and R2, R4, right? We are left with one, I guess. R3 and R4, I guess. Yes. R3 and R4. Great. Done. So here, as you can see, the adjacency form all total is 6. So if I want to derive a formula for this, so it is more of like n, which is here my 4, n into n minus 1 and divided by 2. Yes. And so divided by 2. So this is the formula that is getting derived from this particular state. So if I want to put this here in this formula, so it is coming out as 4 into 4 minus 1, that is 3, and all total divided by 2, which comes to 6. This number of total adjacency, right? Now, this was a very small example, and here to understand, we take small examples, right? But when we are doing implementation or practical, we are making networks for a larger framework, for a larger, we make it for society to use it, right? So the infrastructure is very big. So let's suppose we'll take the example of routers to be, let's suppose, 10. And if I want to put the formula here, so it will be 10 into 10 minus 1, that is 9, all divided by 2. So that will give me 45 total number of adjacency form. So if I look at 45 adjacency form all together, so that will cost me so much of bandwidth, so much of resources consumption, which is basically my CPU. So I don't want it to happen this way. So we have another way where not all routers make adjacency with each other. So what is that way? We'll discuss it later. So if I want to give you an example of how it will look, so if it's this example. So in R1, R2, R3, and R4, let's suppose, okay, let me give you the example. Here we have R1 connected to R2, and then we have R3 connected to R4, right? So I'm not able to make here what I'm trying to do. You will see a full mesh being created here. So that gives us the conclusion that it is asking for excessive resource consumption, where we can see the load in the bandwidth. So we avoid this way, right? And now let's see what we make. So before understanding the concept of BR, B, BDR, DR, and DR others, let me give you a little story. So let's suppose we are in a class, and in every class, we have a monitor, right? So we have a monitor here. The other person here is an assistant monitor. Along with the monitor, we have an assistant monitor. And then we have the rest of the class, right? So the three candidates which we can derive from the story, that is our monitor. The next is our assistant monitor. And then we have the rest of the class, right? Rest class. Now if I want to fit in into networking concept of DR and BDR, so our DR, let's suppose we have a router 1, that is our DR, that is designated router. So our designated router works as the monitor, right? Then we have, let's suppose, router 2. Now router 2 here behave as BDR, that is our backup designated router. So this acts as a assistant monitor, right? And then we have the rest of the class. So the rest of the class, R3, let's suppose R4 and R5 and also R6. Here be assumed as rest of the class, that is our DR others. DR others or drother, right? So now what we do here is, let's suppose there is a topology. Let me pull out a topology for you. So here in this example, let's suppose this is our DR and we are making R2 as BDR, backup designated router, and all rest R3, R4, R5 and R6 we are making them DR others. So here the rule says DR and BDR will make adjacency with each other, like this both will make adjacency with each other. Now all the drawers, this DR, let's suppose R3, will make adjacency only with DR and BDR. They will not make adjacency with all others, all DR others, not with R4, R5 or R6, but it will make two-way state or neighborship with all the other DR others. R3 can make neighborship or two-way state with all the other DR others with R4, R5 and R6. Similarly, all goes with this. Only this DR and BDR will make adjacency with each other, and all DR others with these only, with R1 and R2 as they are DR and BDR, right? So this was a concise lecture about type 2 LSA. I hope you enjoyed. See you in the next one.